Yeah. Thanks. Yeah.
Yeah. So we resumed the conversation about my node regarding the Lempert theorem. So Lempert theorem. And not I do not want to proceed to this conversation in the like the at least lecture style. So Barry, if you don't mind, may I just make the conversation today in a way that we are discussing about this like the node together, not just let me just explain our things just in the solo way. Okay, then let me start to say. What we'd like to discuss together is we'd like to not just tracking the line by line detail. We wanna imagine what's the core of this like the theorem, and then if possible, we'd like to push further that if there are some new result that we are able to get done, then that's the thing that we are now discussing about this note, right? So, but anyhow, our starting point is about this like this statement that if you have a biholomorphic so if the complex manifold is biholomorphic to a convex domain in Cn, then Kobayashi and characteristic distance are the same. So that's the statement we'd like to look at together. So Bertie, is that okay with you?
Yeah. Sure. Yeah. Got it.
Okay, so let's just really naively think about how to attack at least one of the like the approach how to attack this like the problem. Then we first need to think about the these each objects here. These are the Kobayashi and the characteristic distances, and three things are I think important. So in order to handle the equality, these are defined in terms of the complex structure. So if we have a complex structure manifold equal with some complex structure, then always we are able to define Kobayashi pseudo distance and characteristic pseudo distance. Pseudo means, as we already know, that it could be zero. That's possible. That's one thing. And second part, so these are defined in terms of the infimum and the supremum. So in order to talk about the comparison, we should be able to control these extremos. In a sense, the infimum and supremum should be handled. That's the thing. And the last part is so it is related to just the unit disk in C1. So it's complex analysis problem. So even we start from complex manifold, we should reduce the data to just nothing but disk in C1. So that's the like the core of this like the comparison before we talk about the detail. Is that okay with you?
When you mentioned the definition involves complex structure, you mean the Fi belongs to the holomorphic function, which assumes the M has a complex structure,
Yeah.
which uses that M as a complex structure. That's what you mean. The definitions involve complex structure.
Yeah, what I mean is that so we have a complex like the structure on a smooth manifold so that locally we can identify this as an open subset in Cn and we are always able to solve the Cauchy-Riemann equation component wisely and there's a compatibility globally. That's the diving intuition
So,
of complex structure. Yeah,
so the definition of the Kobayashi distance and the characteristic distance depends on the complex structure,
right.
the underlying complex structure.
Yeah, that's actually import like a remark. So even we start from the same smooth manifold. So if we allow to take the one parameter family of the complex structures, for example, then corresponding distances must be changed. That's one feature. And I actually do not think that we even need to require complex manifold, truth be told, in a sense that so manifold is a very like a strong condition, so that one can change the other spaces, include like the variety or like the stack or those kind of the abstraction in the like the topology direction as well. So this is also strong assumption, truth be told. But anyhow, yeah, this is what we know. So Verity, do you have any other comments or is that all okay with you so far about this statement?
Yeah. I'm okay with that. Yeah.
Yeah, so not about the detail. Let's just imagine how to attack this problem. So this is quite clever idea in a way that as we already discussed last time, all we want to just look at is this object that we'd like to call it by the complex geodesic. Complex geodesic just mean that we have a holomorphic map from unit disk. So this is very subtle and important that the domain is just a unit disk in C1. And it maps to the complex manifold in our like the context is just complex domain in Cn that achieves the infimum of the Kobayashi distance. That's the definition of the complex geodesic for arbitrary pair of the given bounded complex domain. So this is just a as elementary property of the intrinsic just invariant distances. So essential part of the comparison, I mean the equality is we just need to find the holomorphic map from D to X that achieves the infimum of the Kobayashi distance. Then we are done. So it's very simple idea. Is that okay with all of us? So that's the idea. And so
Yes,
why?
yes, yeah.
Go ahead, please.
Yes, got it.
So why this is really like subtle? So of course there should be lots of other perspectives that I wanna like to focus on the structure. I mean the of the spots of the D and X. So eventually this is just a map from the unit disk. So that why don't we require X to be the finite dimension? Because all we actually eventually want to handle is kind of the compare, like a composition, right? So that we'd like to compose this F with P tilde or whatsoever, so that it is just convenient to assume this is the domain in Cn, but it seems actually not required. And indeed, that's the case. So there is some progress there. I mean the already the research like which was already done is that just change the setting from the convex domain Cn to convex domain in Banach space over C. That's also possible by applying the same argument, so that we do not actually need to assume this to be just the finite dimension as a sit inside of C, and that's not actually required. But this can be sort of imaginable in a way that because we actually just need to handle just a D, and in that perspective, this I mean our argument is just our domain are just a unit disk, so that it naturally just give our perspective so-called hard disk space. So the hard disk space is just the LP space with just holomorphic maps, so that you just handle everything on the unit disk in C1, so that the codomain is kind of okay. And I already said it's not even required to be the finite dimensional complex manifold. There are already research done so that we can extend the Lempert result to the just a convex domain in just a Banach space, and such a result already exists. That's one feature. Is that okay with you? And but this is kind of imaginable in a way that because the domain is just a D, even though this is very nice, but it can be one can just test whether or not one needs to assume this to be in CN. That's one feature. Is that intuitively okay? I mean, one can at least ask such a like the question. That's what I'm saying.
Uh, Slightly different question. So, the theorem 4.8.12, which says there exists a holomorphic P tilde, which gives the existence of P tilde for a given complex geodesic F. So, once such a thing exists, then we can use the inequality below to compare between the Kara theory and Kobayashi.
Yep.
So that's what is happening as a corollary to this theorem.
Yep.
Now, in this whole part, like right now, the point that you're trying to explain is like somehow like why X can be a finite dimensional space, or why we can expect X to be a finite dimensional space. So that point I did not get. Like X is a complex manifold to start with, if I'm right, is right. So if X is a complex manifold. So uh, what is the reason that you are talking about having X to be infinite dimensional or finite dimensional? I did not get that idea, like because so far we have not seen any infinite dimensional complex manifolds or any such manifolds as such. So that's the reason why something like that we have to think about. Do you mean for even for such spaces the result is true, or what is the thing that you have to know at the end of this?
Yeah. I loved so for today and maybe probably also next time. I'd like to make such a like the conversation. I think this is more beneficial rather than just tracking just the detail. Two clues basically. So the stances here only requires the complex structure. This word is quite subtle. I never meant this must be finite dimensional complex manifold. So even for the infinite dimensional complex manifold, and one of the good example from complex geometry and topology is that I think CP infinite dimensional projectives, CP1 sit inside of CP2, that sit inside
Uh,
CP3, that sit in
uh,
CP4, and we can just keep doing it to just make everything sit inside of CP infinity. This is infinite dimensional complex manifold. It has its own feature. And this definition works clue, so only requires the complex structure, and it doesn't require to be the finite dimension to pose the complex structure. This is one reason. And second reason is coming from the structural.
I'll just add one point here.
Mhm.
So when you mention that it requires only the complex structure, only the manifold, either finite or infinite dimensional, having a complex structure makes us to look at the set of holomorphic functions from D and onto D. Now, using that, we can now talk about the Poincare distance in the disk D. So whether it doesn't, so the way we have defined it doesn't matter whether it's finite dimensional or infinite dimensional.
Right.
We are using the holomorphic functions into or from the Poincare disk, and
Yeah.
using that to define a metric on the manifold. So, that makes the definition suitable for any complex manifold as long as it has a complex structure, irrespective of the dimension.
Yep.
That's my understanding.
Yeah, I totally agree with you. And Barry, if you also have your own imagination or thought, please feel free to share. I'm very happy to listen and learn from you.
Yeah, I think we can define Kobayashi in. Okay, am I audible?
Yeah, we can hear you. Yeah, let's go ahead.
Yeah. So we can define Kobayashi pseudo distance on the complex space, right? It does not mean that the space is finite dimensional or infinite dimension, right?
Yep. Yeah, so that's the sort of point. So we just naively just assume this is just a C, just the n dimensional, and it's
Am I
actually,
correct?
but we are just saying n does not need to be even finite. That's a
Okay, thank you.
finite number. Yeah, that's one thing.
Just one small. The n that you have written here, does it signify the dimension of the manifold M, or is just like it is representing finite partition of the paths between X and Y?
So mathematically speaking, all we know is just this definition, for example, and as long as we are able to solve the Cauchy-Riemann equation, then we are still talk about this one for sure. And we just pointed out that there could be the application that we can still say something about these two distances, and we do not care whether or not there's a compatibility of those two dimensions. This is dimension one, this is arbitrary dimension, and why
Ah,
don't we put the finite dimension? That's the feature.
oh, the first point is clear to me. I interrupted you before you were sharing the second point.
Mhm. Yeah, so
Uh, uh,
yeah, if there were some other comments, let me know. Back to Alan's the comments regarding this theorem. So think about what this statement means. So our input data is complex geodesic, meaning the holonomic function from D to X achieves the infinite Kobayashi distance. That's the meaning. Then all those the duality of principles are about guarantee such like a P tilde. But what's the subtlety? We change the map. I mean the spots from X to D again. Why do we need this? Because we only care decomposition. We never use P tilde alone. All we want to use is decomposition. So what do we actually have from D to D? So the intermediate stage, we don't need to make X to be finite dimensional at all. That's the
so
second.
the extremal problems and other things that are defining that we're going to handle and so on, we are basically dealing with this to be a finite, like just D alone. We are not dealing with X.
Right. Right. So with this perspective, so if you look at the tools here, this is funny. So now look at this again. So we just think about the complex Banach space. So we know the sort of the spirit of the Banach space is sort of the monster space compared to the Hilbert space, right? So we already kind of assume that this is already infinite dimensional complex vector space. So that already the tool is we adapted from the very like the fancy tool of from functional analysis to handle the infinite dimensional complex vector space. So the tool is already quite fancy, that we need to beyond the finite dimensional like the tools, not just a linear algebraic argument. And even for the Lempert original like the argument, also strongly rely on the Banach space argument as you eventually just rely on the Han-Banach theorem. But I want to just point it out that so we already have some infinite dimension like the perspective. That's one feature I'd like to explain so that what we can then expect further. So for example, so if there are some variation or the extension of this theorem, then we kind of need to recognize that it might not require the finite dimension for the statement, even though our classical like the statement should be written in that way, but it's just a convenient assumption, but might not be necessary. That's one thing. This is one feature I want to discuss. Yeah, let me know if you have other comments.
Now I get the point. That is like this M is biholomorphic to convex domain in C, and now we can that finite dimensionality first time comes at this point, which is not necessary. That's the whole remark.
Yeah.
Okay. Okay.
Yeah. Yeah. Please let me know if you guys have any other comments. Yeah. So
One thing that is not explicit for me so far is like I understand like now the goal of proving the Lempert theorem is reduced to finding that P tilde with those properties, and you have said that that P tilde's existence is given by solving this extremal problem. Am I right?
yeah, so that's the
Uh,
perspective I'd like to talk about for the next like the
okay,
core of the statement.
okay. So
The
I'll just
first
hold.
thing. Mhm. Yeah, go ahead.
Sorry. My only doubt is that like I've not exactly figured out how that solving that extremal problem is exactly connected to the P tilde that we wanted. So I'm just looking at so probably you will like, be explaining at that. I'll just hold on for
Sure.
some more time, listen
Sure.
to you, and then we'll get back with more questions.
Absolutely. So yeah, now I'm happy that you are now curious about the how to apply the principle of the duality to achieve this. This is yeah. So this is the key spirit of this like the approach. Verdi, if you have any other comments or so remark, let me know.
Yeah, I don't know remarks right now.
Sure. Sure. Yeah, but before I move on to the Ellen's like the very like a necessary perspective to figure out the necessary information, I wanna just think about application first. Just the application. So not all, how to establish this theorem. So why this theorem I mean the why this argument would be important. I mean, not just saying, well, now so that we have equality. So what? What's the point? So according to this approach, so we know already, according to this theorem, all we need to get is the complex geodesic. If we have a complex geodesic, that determines this P tilde from retract that solves this problem. That's the idea. And so that we first need to get complex geodesic, then by saying blah, 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 when we have something. That's the idea. And the definition of the complex geodesic is what? So this is the holomorphic map achieves the Kobayashi distance. Is that okay with you? So of course we already know. So as long as we have complex geodesic, then we can establish this. But I'm not talking about this implication. I'm just talking about the very first line. So if we have a complex geodesic, that means that we have a holomorphic map from D to X that achieves the Kobayashi distance. This is a definition of complex geodesic. Of course, the reason that why people previously called this by the geodesic is that this should be coincide with the Poincare geodesic distance, but let's do not think about like the Riemannian geometry perspective. I'd like to think about why this matters first. So I'd like to show you one of the just a reference, just hang on. I wanna just show you that one. So Kobayashi metric Winsler, just hang on, because I think this could be very likely helpful. So let me first post this on the chat screen first, and then try to show you how I figured out the reference in a way. So one of the greatest, like the mathematician in complex geometry is S.S. Chern. You might heard about the name in the very different like the context. So you can just assume Finsler geometry is now what we are talking about. So you can just later look at this definition. But so Kobayashi distance is the distance coming from the Finsler metric, because the Kobayashi-Roida metric itself is a Finsler metric. What I want to show you from this, like the article, is, let me directly jump into this one. There should be here. Just should be somewhere here. Just sorry. Yeah, so I'd like to talk about what he said about reference 11 first, and then I will show you the paper, of the reference 11. So let me just now search the number 11. There should be somewhere here. Yeah, complex Finsler geometry here. So, and this is a corresponding reference. And what he said is Finsler geometry will be most useful in the studying of complex domain, because so always we can associate to those two pseudo metrics. And he just want to point it out that the explicit example, that means the explicit formula of the Kobayashi metric and the Kobayashi distance, just look at this reference 11. That's the key feature of this one. Is that okay with you? So that he just pointed out that the Finsler geometry could be useful to study complex domain. And I just start to say, we don't actually need to require to the domain to be the finite dimensioner. And according to SS Chern says, so there is the explicit example. So let us first look at that together. So in that the paper, you can also just simply just search from Google, and let me just show you that. And such the approach is not still very successful in my opinion, in a sense that because this is a very hard question. This is interesting but hard question. So let's just look at this the two-dimensional the domain. So expert in several complex variable usually call this by so-called the Turing domain. Let me call the name Turing domain, and I prefer to call this by the egg domain. And this m is the positive natural number. If this m is strictly greater than equal to 1/2, this is convex in the just elementary sense. If m is strictly less than 1/2, this is not convex. But at least this is always weakly pseudo-convex, so that there is complete Kähler-Einstein metric of the negative scalar curvature. But anyhow, so let's look at this example. So now you see how ugly the form of the Kobayashi distance. This is a metric like the description, not the distance description, by the way. And how can we describe the metric explicit? So for the ellipsoid or the Turing domain or the egg domain, Kobayashi distance can be represented in this explicit form. This is what this reference says. And how can you find it? According to Lempert theorem, we know all we need to find is complex geodesy. And you see, this triangle means the unit is in C1, so that the approach is just nothing but finding the complex geodesy. And in this paper, they just call it by the extremer map. Now you see the reality. So that if we are able to find the complex geodesic, then we are able to describe the Kobayashi metric. And I think as long as we have a complex geodesic, then we are also able to describe the Kobayashi distance explicit as well. It's just a skip. Is that okay with you? Another important one application of the complex geodesic is that if we are able to determine the complex geodesic explicit, then we are able to describe all these object explicit. And as far as our known the references, this is the only possible approach to find the explicit formula of either the Kobayashi distance or the character distance. At least for the bounded complex domain, they are the same. And we'd like to determine the metric and the distance explicit, then we need this. That's one also important feature. So please let me know if you have any other comments. So what I just found is, let me also put that in the chat screen. This was the reference I was looking for. So in that sense, so there could be the lots of interest the questions in a way that, so even for the finite dimensional complex the vector space Cn, and if you look at the bounded domain, by just applying the argument of the Lempert approach, if we are able to find the complex geodesic explicit, then this has a very important implication for that domain in a way that we can determine the metric and distance explicit. This matters. That's the one thing I want to also say. And I just want to also extend the perspective that if there is already a known result of the explicit formula of the complex geodesic, then one can also try to extend that, push the result to the infinite dimensional situation. So that you can kind of imagine, if we know the complex geodesic explicit inside of the domain in Cn, then why don't we just push to the infinite dimension? Then that's also a decent the result to also try to attack. That's the second part I want to also share, so that the determining the complex geodesic matters to get new result, because so far as I know, this is the only possible way to determine the formula of Kobayashi and the Kobayashi distance and the metric. So please let me know if you have any remark or comments on it. Does that make sense to you? Or no?
Yeah, I have a question. So once if you have a complex geodesic with respect to Kobayashi distance, so we can get a formula for the Kobayashi distance, right?
Right. So
what about the carothorary? Is it possible to get the carothorary formula from existence of the complex geodesics for carothorary distance? Sorry.
That's a very good question. So I have just a statement that all I know. I actually want to know further, but I just want to say, in the class of the convex domain, we need to rely on this result, right? So the formula of the
exactly. Yes.
Yeah, this is very unfair to say, but that's one thing I know. And the second, the information. So if we look at the definition of the characteristic pseudo distance, then this is defined in terms of the supremum from the given complex manifold to the unities. So if we apply Montel's theorem for arbitrarily, what I know is just a finite dimensional complex manifold. I never thought about infinite dimension in this context, but for finite dimensional complex manifold, there's always the extremer map if we fix the pair. That is guaranteed. So, but we don't, I don't think, we just know the distance, but not the explicit formula of such an extremer map. So if we know the extremer explicit, the form of such an extremer map, then we also know the character distance, even that's the outside of the convex domain. Existence follows from the Montel theorem. But
I see. Yeah, exactly.
So that I think this is a very interesting question in one variable complex, several complex variables. So that can we determine explicit form of the holomorphic functions nicely? And this case we just call it by the complex geodesic.
If I understand whatever the point that you're trying to tell us, if you know the complex geodesic, I just want you to hold on this page. If you know the same page, whatever you're showing, the definition of paratheory and covariant distance.
Okay. Yep.
Okay. So if you know complex geodesic, which is basically a map from D to M,
Right.
and which basically picks out a suitable F such that this delta, like rho D, rho subscript D, which is the Poincare distance, and is both of them intersect. So for such an F, if you are able to find such an F and know that explicitly, which means DM, the Kobayashi distance, can be described explicitly. That's the whole point that you're trying to explain. And to Bharati's comment, your reply, if I understood correctly, the existence of P tilde, which is what is giving the equality eventually.
Yep.
We know the existence, which is the map from M to D, reversing the domains and codomains.
Right.
We know the existence, but we do not know the explicit thing. Probably, if we know it explicitly, then we can think. In such cases, can we give explicit expression for characteristic?
That's good point. I think that's also important. Like, yeah, thanks for that like perspective. I totally agree. So that can we also have a further information rather than just the existence like the result. That's a good thing. As you if that's what Barrett was aiming to say, yeah, I appreciate that comment. I actually didn't think about that way. Yeah, with that perspective, I think this is very reasonable to look at. For example, so for this two-dimensional bounded convex domain, let's just assume, but if you just search the non-literature, so there are two papers. One is if m is greater or equal to 1/2, so the convex domain. If m is strictly less than 1, still there's an explicit formula of the Kobayashi metric, by the way, so that is worthwhile to look at. And it's coming from the complex geodesic, basically, but at least if you just look at what this paper did, so there is no clear description of the P tilde. It's just solving just an extreme problem of this infimum of the Kobayashi pseudo metric, so that it's very worthwhile to try to link P tilde of the argument of the finding the Kobayashi distance. Yeah, I think that's also very valid because we already rely on the structure that they must be the same. These two distances are the same, and so sort of we already use P tilde behind.
Okay. So even in such cases, we don't know the Kara-Theory distance, but we expect like they are equal.
Yeah.
So probably we should be with that data of dx and cx being equal, we should be able to get an explicit expression for the P tilde. That's like tell something about.
Yep.
Just to add to the last point that I mentioned, how did I come up with it? The idea is basically in the definition itself. Somehow we want to choose nice enough holomorphic functions such that the Poincare distance and Kobayashi distance, similarly, Poincare distance and the Kara-Theory distance behave well. So one is the complex geodesic, which connects nicely in the case of Kobayashi metric, coincides in the Kobayashi metric. Now the converse is what is needed for the Kara-Theory distance, which is the P tilde. Now, basically, you mentioned the last remark. The way I understood this, if the complex geodesic has an explicit expression, then the Kobayashi metric has an explicit expression. So it's very natural. I thought if P tilde has an explicit expression, can we tell Kara-Theory metric has an explicit expression, or the other way? If the Kara-Theory distance, even from your point, it's much more. Even if you know the Kara-Theory distance explicitly, in the case if it's equal to the Kobayashi, can we tell something about P tilde explicitly? Yeah.
I do not know the answer, but I really appreciate this, like the imagination and the comment. Yeah, I think that's worthwhile to point it out. Yeah, thanks. Yeah.
Especially the maps are not biholomorphics or inverses or something. It's just from one-dimensional complex space to any dimensional complex.
Right.
Interesting.
So it seems now we have a more motivation to look at the setting. So now let's look at the setting together.
Exactly.
All right. I think I should show you from somewhere here. So now let's look at probably just hang on. Yeah, so let's just look at this part together because this will give you some big picture. I'd like to look at here. I assume you can see my cursor. So first, First, so we have a Cn. Even I already mentioned the Cn might not be really necessary, and indeed the Lempert theorem should be or was already extended to the complex Banach space and the inside of the complex domain. But let's just assume Cn for our convenience, so if we assume this is convex domain, and we also assume bounded convex domain, so that we can also talk about the topological boundary. So then this is just a natural like the map that we use the vector space structure so that I assume you can geometrically imagine how it looks like, right? So that we just look at the ray in the direction of the z, and we just measure the supremum of the arc so that we just try to extend in the maximal way. So that's the meaning. Is that okay with you? So then this behave as a so-called Minkowski function. So as we already discussed, this is at least not the norm. So could not be not very much useful as a norm of the complex Banach space. However, if we assume these two, now this assumption plays a role in a way that first we can realize the bounded convex domain as P of z Minkowski function is less than 1. And if you try to establish this equality, then it is a good exercise that you can just try to show that convexity assumption must be used. That's one thing. So that if you now ignore the convexity, then still we can describe this for sure, but we just do not have the equality. That's just a logical like the part, so that in such a case, some research like the imaginations, then still what can it tell? So that's one thing. But I also now you understand what I'm talking about. So by using the convexity, now we can achieve this. Then because of the boundedness assumption, we can also nicely describe the topological boundary. So that if you now look at the Theorem-Minkowski functional defined in this way, so and denominator we divide by this guy, so that we just think about this denominator as an effect of just p sub x equals to 1, so that we just choose the point from the boundary, which is compact, so that we are able to achieve the supremum. So those are, in that sense, logically related, so that this is continuous function, but we'd like to assume, then we have just a compact like the choices, so that we are always achieve this like the supremum. And the reason is that we actually assume these two altogether. So, and this is also required for the complex Banach space as well. So for the complex Banach space, so that the subset we are still assume bounded convex domain. This is okay because we already have norm, so that we are able to describe the boundedness for sure. But I didn't mean that so that this is a necessary assumption. This is just a very valid and intuitively like the okay point. However, there should be the way to figure out if this is equality is not the case, then what can we still talk about? So, but anyhow, let me now still move on. But at least now you see why we assume bounded convex domain. And we have a Theorem-Minkowski function. Then we have a corresponding Minkowski functional. So that is defined on the complex Banach space that we will use for the Hardy spaces eventually. So, and there are lots of possible choices when P is equal to either 1 or infinity or whatsoever. So that as long as we have this guy, then we can describe capital P. That's we call the Minkowski functional. And we also have the dual Minkowski functional as well. So now we have a P and P star, so that at least we have a setting. We already just recognize that at least we can apply this theorem. I mean, the pure principle of the duality. And what's the point? We know that at least we should be able to solve the dual problem. That's the one benefit we'd like to definitely take. And then if we can say something regarding the original problem, or where is it? Original problem, linear experiment problem, then the information of the dual experiment problem also plays a role. That's the spirit of the principle of the duality. So, and I didn't mean that I explain every step by step, but you can now have a motivation to think about so how to apply this theorem, so that linear experiment problem and dual experiment problem are related, and at least dual problem should be solvable. And at least if we can solve the linear extremal problem, then we can say something. At least P of F equals to the linear solution of the linear extremal problem. P star of U solves the dual extremal problem, and so on. Then now let me just go back to Alan's like the point. Then how did we use this? So the way to use this here. Now you see how tricky this is. So bounded convex domain, so that we have a Minkowski functional, and the choice of the complex Banach space is the hardest space when P is infinity, and this just a notation of n just means each component, there are n components, each of them just satisfy the hardest space with P equals infinity, so that this is what we care. This is the meaning of the complex geodesic for this pair of x and y. So suppose we are able to achieve that infield by this holomorphic map from D to X. That is the solution of the linear extremal problem. So you see, we actually have everything. So that if we formulate the principle of the duality, we already know we are able to solve the principle, we are able to solve the dual extremal problem. So the lack of the information is the solution of the linear extremal problem. Then where is the solution of the linear extremal problem? Is the complex geodesic. So and then in the case there's some like the comparability condition between M and M star. I mean the solution of the linear extremal problem and solution of the dual extremal problem. Then we know how to compare. And so what's the benefit? So for example, because everything is actually working over just the disk in C1. So therefore, we can apply the quotient integral formula very nice way. So it's actually working on the hard disk space. And then we just apply just a bunch of the complex analysis, just argument, so that we can have some nice control. So as all of you already pointed out, so we already have some control of the capital P of F and P tilde of U already, so that we can, and then we just establish the P tilde just as existence result. So that's the spirit of how to use this. So let me just summarize in very like a simple way. So how do we use the principle of the duality? It's just we just want to realize that as the solution of a linear extremal problem, then we have all control of the principle of duality. Then just write down everything explicit in terms of the quotient integral formula, and that's it. So yeah, that's the key theme. And still, this is just an existence result, so that there should be some subtle point that one can look at. So whether or not one can actually say something further, rather than just a complex geodesic as a solution of linear extremal problem, and also the corresponding just a map, or can we push kind of further about knowing this from this argument? That's one feature. So not just that this is just a theoretical application of Hahn-Banach theorem, but we have some nice control about the quantities. That's what I mean. Talking about just this guy. So we have certain control already. And then we already know what these are. And this is complex now geodesic. And also we have still control. So that you can look at each of them and what this information really meant, and there should be some possible like the further directions to like the handle. So also let me know if you have any other imagination or remark or comments. But I think my point is very clear, right? So this just means the complex geodesic. Or I was so
Yeah, here I have one. Where we using boundedness of boundedness? Where we are using boundedness here?
Because it seems like the voice seems now there's a lag there, so it could be useful. You can just type your like the comments or question on the chat screen. But if
I think his question is, where did we use?
Mhm.
I'm sorry. I think you understood. It's about the boundedness of the domain. Where did we use it?
Yeah, so boundedness of the domain is used over here. So let's
Am I audible?
now I can hear you. So let me get back that answer. So
Audible right now?
sorry.
Am I audible?
I can hear you, but time to time there's just a lag. So could be useful if you just type your like the comments on the chat screen so that we can clearly precisely discuss. So the boundedness, so convexity is used to establish this equality, and the boundedness is used here. So that when we describe the dual Minkowski function, then we divide by Minkowski function, and we just realize that as a topological boundary of the given bounded convex domain. So that now this is compact, and now you see we use the boundedness so that this is compact like the domain, so that we can choose this supremum as just a maximum. But this might not be. Again, I am very suspicious that we don't actually need to assume neither of them, but this is way to use this part, so that you can now look at, so that there's just the argument of the point on the topological boundary with the supporting hyperplane to just realize this like the dual Minkowski function, and then by using that, even we define in this way for the dual Minkowski functional, but the reality that if we want to use the Cauchy integral formula, then in fact we use a dual Minkowski function as well in this way. You see, it's sort of the Cauchy integral formula, and here we already use the boundedness of x for at least for the convenience. But again, yeah, we need to be suspicious.
Yeah. So yeah, exactly. I got it. Your point. And thing is that Lempert theorem is for just a convex domain. Right? M is biholomorphic to convex. Right? So how do we compare with the boundedness? Is it true that every convex domain is biholomorphic to bounded convex domain?
I also very appreciate that comment. So as you pointed out, so for example, if you just look at the upper plane in C1, Poincare upper plane and the Poincare disk, so one is bounded, the other is not. So it is very, very subtle to assume boundedness. So the statement is very subtle. So according to Lempert theorem, if it is biholomorphic to any of the so of course this statement is a convex domain, but we informally assume it's a bounded convex domain, because if it is just biholomorphic to Cn, then these two are just a zero, so that we should find one representative of the bounded convex domain for sure. But this is very subtle, right? So because time to time we might just are able to find a non-bounded, unbounded, just a domain in Cn. In such a case, then what can we say? So I actually have no idea. So the information we are using is that these two pseudo distances and pseudo metrics are defined in terms of the complex structure. So therefore, boundedness is very subtle. So because these two metrics are only requiring the complex structures, right? Complex structure. So, and whereas the statement, I mean, the class that we'd like to handle, in fact, boundedness is not really necessary in comparable to the complex structure. So yeah, that's what I just have in my mind. But yeah, I do not have a very clear like the perspective how to think of. But yeah, boundedness is very like the unknowing assumption. So yeah, so this could be annoying in the following way. So if I just think about just a Cn, then we know this is zero. And if this is a convex domain, then this must be the case by just applying the same argument. However, I just assume in that case, it's just a zero. So I just split into just two cases. If it is bounded convex domain by holomorphic convex domain, then apply the Lempert argument. If there's no way to find the bounded like the convex domain, I mean representative, then it should be just zero. So the conclusion holds in that way, but I do not know how to think elsewhere. So that's my perspective. You know what I'm talking, right? So just split into two cases, and either two cases, this is at least the case. But I want to actually think about this without the bounded convex domain, boundedness assumption. But this, like the argument, already used the boundedness in the argument. So if it's not bound, if it is not bounded, then it's just a zero for those two distance, and the argument is over. So and otherwise apply this. But I don't really like it.
Yeah, last point I'm not getting. So are you saying if it is unbounded, then the Kobayashi is carotheric is with the vanishes, or?
Thanks for that comment. Here is what I'm saying.
If it is Cn, then it's zero. That I understand. But there are unbounded domain whose cathode is never zero, and
I agree with you. So I actually agree with you. So if there's a outside of the Cn, which is unbounded convex domain, then what can we tell? So mathematically, or I really convinced because of my study. So is the argument of this functional analysis like the technique, and it requires the boundedness. So as you pointed out, so what if we have a unbounded convex domain, which is never biholomorphic to bounded convex domain, and it's also not biholomorphic to Cn? Then what can we tell regarding these two? I have no idea. But it's just my lack of the knowledge. It might be already known. I believe this is a very like the well stated like the fact, so that it's very good to just track that if we look at such like the class, then how can you argue this? So yeah, I also approach.
the reason why I asked that question in a Riemann mapping theorem, if you have a simply connected domain, we can always make it biholomorphic to a bounded simply connected domain, right?
Yeah.
Yeah. So I asked this related to that.
Of course, we have a Riemann mapping theorem for just a one-dimensional case, and we lose such a like a theorem from dimension 2 for sure. However, let me just look at the reference, which is most like the canonical reference. I think this is, I assume Bertie already have it. So this is very good reference to keep for the several complex variable. And there must be the statement of the Lempert theorem, I assume. Yeah, here there must be it. And the argument should be different from the principle of the duality. So but let's just look at it. 308, 358. Complex geodesy, we know what this is. Let's just skip complex geodesy. This is. I just want to look at the statement of Lempert theorem from here. It seems this also reference also use the same argument. Yeah, this is a statement. This is a statement. So I think it's good to take a look. Yeah, since what I said is mathematically correct, but there's some gap of my understanding. Yeah, this is what I explained in my note. Yeah, please take a look, and if you have a better understanding, let me know. So yeah, I mean not right now, but via the email or next time. So that's also good to discuss together. Let me just go back to my note. But I would like to clarify various like the points. So can you just repeat your like the sort of like the point about the consideration of the Riemann mapping theorem? Can you just repeat again, please?
Hello. Yeah, I'm really sorry for that. Network issues for me. I'm not in the department, so it's network issues for me. Yeah, did you got my questions? My points?
Yeah, so let's just repeat. So can you just repeat your like the point so that we can discuss about it?
Yeah. So we have seen already in Riemann mapping theorem that every simply connected domain we can make biholomorphic to a bounded simply connected domain, right?
Yeah, just a disk.
Yeah, that is theorem. But in the proof, initially in the proof, one of its proof I have seen, they have started with a bounded simply connected domain, and then they will make with this biholomorphic to unit disk.
You're talking about the Riemann mapping theorem, right?
Yes, exactly.
Okay.
So I have asked related to that, is it possible to make unbounded convex domain biholomorphic to a convex domain, a bounded convex domain in CN?
I understand your point. I think it's subtle in the following way. So I definitely understand what you're talking about. You're asking about the bounded domain representative or the unbounded like the domain representative. So in if there so in if there are some possible application from this argument that we are actually say something regarding this like the choices of the representative. That's what you ask, right?
Could you please repeat?
So upper plane is unbounded, disk is bounded. So some of the complex manifold might be biholomorphic to bounded domain. Some of the complex manifold might be biholomorphic unbounded. You are asking if this like the application or the argument so in detail could be related to the finding the either the bounded representative or the unbounded representative. Is that what you mean?
Yes, exactly. Yeah.
I don't think this could be relevant. I mean, for this, like the detail in the following ways, because this but could be. So please just try to be suspicious of what I'm saying. But these two objects are defined in terms of the only the complex structure. Therefore, so it doesn't care whether or not we are able to find a bounded domain representative or unbounded domain representative. It doesn't matter. So that's why. So Poincare distance is the same on the Poincare upper plane, which is unbounded, and also the Poincare unit, which is bounded, but doesn't care. So that we can just change this with a rho sub h if you want. It's unbounded representative, but it will not change anything in terms of these quantities. So therefore, it is nothing to do with finding the bounded or unbounded representative for the statement level, but the detail uses the bounded domain to describe the Theorem-Minkowski function nicely. That's just what I meant. And there could be some like a deep relation behind, but I don't know at this yet. But yeah, is that
Yeah.
question? I just said
Yeah,
I
I got
don't.
it. I got your point. Yeah.
Yeah, thanks for the good question. Um, so I think so now we have some like the motivation to look at this like the node with the detail. So I don't wanna just make the conversation and discussion about this node just at least one time further next time. I'm not just saying we need to track each line by line, but if like ever your motivation, you can just look at and we can try to image and discuss. And one like an interesting project, in my opinion, is to determine the complex geodesic explicit some reason like the domains. I mean, with the reason like the symmetries, there would be able to determine the complex geodesic explicit, then there's an implication. I think this is also a good project in the complex analysis and several complex variables. So for example, on the annulus in C1, I bet there's an explicit formula of the Carthy-Odori and therefore Kobayashi metric, meaning that there is a complex geodesic, and so on. And if any of you are interested in that direction, I can also investigate together so that just list the known result and we can try to attack together. And at least we will talk about this node once more. I'm just at least once more. And if we feel we are okay with it, then we'll move on to the next topic. I will also share the node and discuss in this way. I think this is beneficial for us. So if any of you have any like further comments or questions, let me know and let me start the record then.
I think will be good to go through this Lempert theorem once again, in the sense like would like to go through it ourselves and then probably share our understanding of what these theorems are like what are the main ideas of it, how they are interconnected, and how they are come together to and the proof goes. So that like the Lempert theorem is clear. So in that context, I would like to go over it once. One. Second, yeah, you have something. Yeah.
Then here's my suggestion to Ellen. I didn't mean that, so because I know you are very, very busy for sure. So, but I think it's good to learn by just presenting detail, right? So you can present the proof next time if you don't mind. And I didn't mean that you need to complete the whole argument, but you can try to track the detail, and you can present your summary and just look at the detail. And if there is some like the gaps, then we can try to clarify it together. How about it?
Yeah. Two things. One, like let's not record that session. One. Two. Probably if Bharati is available, has some time, we'll probably sit together for 1 or 2 hours, so that we'll be able to break things down together much easily, and
Sure.
then it'll be easy to present. So
Absolutely.
Yeah, yeah, yeah. Yeah, we can do it, and we can do it.
great. Great. So next
Yeah.
week we'll try it.
Yeah,
Ah.
exactly. Yeah. Yeah.
So by the way, I will make the travel next like the week entirely. So we should skip the this seminar next week, and so that we will meet in 2 weeks, not next week. Yeah.
The second point I had is like, so basically you're mentioning about explicitly calculating the complex geodesics for certain examples. And probably I missed it, but I'll just put it. So the idea is like trying to understand how it's done in the complex ellipsoid in C2, that paper. Try to understand the crux of the ingredients for the proof there. And then try to and then try to prove see what are the other places where we can try this idea or some other idea and calculate explicitly the complex geodesic and thus the Covey symmetric for some spaces. Is that maybe we can add.
Here's a comment that I will provide the further information without the record because I don't want to share the very precious information to
I'm
the
sorry.
general audience.
I'm sorry. Yeah.
So just let me just finish by saying the following. So yeah, so if we understand that like the detail of the description of the complex geodesy on the Turing domain or the egg domain or the ellipsoid,
Correct.
okay, then I already know there is a case that we can extend. So if any of you are motivated to look at that, like look at this direction, then I'm very happy to discuss further. So, but for some of the information, I want to be confidential so that I will not make the record for that. So
Understood.
it's beneficial for us. So yeah,
Understood.
yeah.
Perfect.
Let me now
Yeah.
stop to record here.